Hello everyone, welcome to the video demonstration of RAMAN audio inference using Neuromorphic Cochlea on the Epinix TI60 FPGA board. So this is the hardware demo setup. This is TI60 FPGA board. Power is supplied through this power supply cable and the programming is done by using this micro USB cable. A I2S based microphone is used to record the audio data and the complete architecture of audio inference is deployed on this FPGA board. Output is observed on two RGB LEDs. The first LED is a silence detector. Here 1 represents silence or noise and 0 represents a keyword. The second LED represents the done signal of audio inference. The microphone is connected to the Epinix board using the GPIO pins, and we have assigned the predicted class and silence detection bits to the Arduino digital IO pins, and the transfer of these 5 bits to the PC is done using Arduino and serial read function in MATLAB. Here is the complete hardware end-to-end flow diagram. Microphone receives power supply from the FPGA board. It works at a clock frequency of 2 MHz. Clock is supplied through I2S module. Audio signal from the surrounding environment is detected by microphone and the bit-by-bit data is passed to I2S module. The I2S module converts that bit-by-bit data information from the microphone into a 16-bit audio sample. This 16-bit audio sample and an enable signal is passed to CARE module. CARE is a pre-processing block that extracts frequency information present in the audio signal. It has 30 filter banks, so it gives 30 ISC output values with address information. Wake up unit is a module that turns on the RAMAN when a keyword is detected. It outputs 1 when a keyword is detected and 0 when noise or silence is detected. In case it detects noise or silence, it also enables done wake up signal that bypasses the classification process and directly gives silence as the final output. In case a keyword is detected, RAMAN is enabled. RAMAN is a sparse ML accelerator that classifies the audio signal out of the 12 output classes. That output class information is passed to output class predictor module, which produces the final predicted class and silence detector signal.
Yeah, that's a quick overview about the individual modules and their connections. This is the digital cochlear model block diagram. It emulates the functionality of human ear. Basal membrane inside the human ear acts as a frequency spectrum analyzer by vibrating at specific locations based on the input frequency. These vibrations are then captured by the inner head cells and transduced to neural signals. So after receiving the 16-bit input audio sample, we'll begin the pre-processing and it will generate a vector of 30 numbers. Then we will perform the max pooling over a frame of 500 consecutive audio samples. Since we are using a sampling rate of 16 kHz, we will end up with 32 such vectors in 1 second, which essentially forms a 30 cross 32 matrix, which we call it as a cochleogram. After that, we will summarize all this information by accumulating these 32 vectors and form a single vector of 30 numbers. This combined vector will then be forwarded to the wake up module, which generates a wake up signal to the accelerator. This is the top level view of the hardware accelerator. It has different components. Instruction memory, which stores the instructions generated by the instruction compiler. Global memory stores the parameters and the input and output activations of different layers. It has a controller. It has 5 different slave wings. Convolution. It supports the convolution 2D, depth-wise, point-wise, global average pooling, and fully connected layers. It has a processing element array. It is basically a 3x4 arrangement, and it is reconfigurable to perform the computation for all the layers. It has data and parameter cache to exploit the sparsity, and data sparsity logic to exploit the sparsity across input layers. And the post-processing block performs the bias addition and quantization, and also used for global average pooling. Now let's start the GUI. This is the main window. Here you can observe 4 buttons. You can see the end-to-end flow of RAMAN audio inference, its design highlights, resource utilization, and the demo. So it is basically a maze game. It has 12 different functions and that are assigned to 12 different classes. You can observe the functions over here. Unknown and silence is assigned to none function. Yes and no for play and quit. Up, down, left, right are for different directions. On and off are to start and exit the game. Stop and go are to pause and resume the game. Here you can observe 3 statuses. Keyword detected displays the current spelled keyword. In status of RAMAN displays whether the RAMAN is active or not. Game mode displays whether you are playing the game or it is in pause mode. Now let's start the game by saying on. On. So now we can observe that the game is displayed on the screen. So let's play the game. Down, 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 right, down, right. So now let's check the functionality of stop and go. Stop, And now you can observe that the game is in pause mode.
Right, down,
Yeah, here you can observe the status of keyword detection and the status of Raman. There, it's like the keyword is being detected. The player is in the same position because the game is in pause mode. So now let's resume the game and continue it.
go,
Now the game is in play mode. So let's complete it.
down, down, left, down, right,
Yeah, we have completed the whole game. So if you want to play again, we have to say yes. Let's say yes.
yes,
So now you can observe that a new game is loaded here because we spelled the keyword yes. So let's check the functionality of off keyword.
off,
Yes, you can observe that the keyword off is detected and we are out of the game. So that's the video demonstration of Raman audio inference using Neuromorphic Cochlea. Thank you.